My name is Ryan Fortner, and this is my presentation of Physics 2, Lab 3, Magnetic Field of a Bar Magnet. First, I will introduce the purpose and key concepts behind the lab. Then I will detail my experiment, including the design, assumptions, and data I gathered. Then I'll go into the computational model, including the code, the model, and the results. And finally, I will conclude with the two what-if questions. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare my measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. A quick result preview: I found the in of the R that that the dependence is based on to be 3, which lines up with the Biot-Savart law. I also found the dipole magnetic moment to be around 17.6 amp meters squared. The first key concept that's important in understanding this lab is how a cross product works. Basically, you cross two vectors and you output a vector that is orthogonal to both the input vectors. Then there's the Biot-Savart law for a magnetic field, which is the equation is on the slide. And depending on the relationship between r and the velocity, you have a zero magnetic field. It's measured in units Tesla. Then there's the magnetic field of a dipole. The equation's also on the slide here. It's more accurate when you're farther away from the dipole, and it simplifies if the vectors are parallel or perpendicular. Then there's the magnetic dipole moment mu. The direction of the on-axis field is the same direction as mu, and is also the same direction as a conventional current. So for my experiment, the system is the iPhone with the magnometer app, which I used PHYS. And then the surroundings are Earth and the bar magnet, as those don't move. I used an Excel sheet for data collection and my graphical analysis. For this experiment, I assumed there was no human error on my part. I assumed that the magnometer is accurate. No other nearby magnetic fields are present, that I aligned the iPhone correctly, and there's no large steel or iron objects nearby that could manipulate the field. I also had to find the net magnetic field in New Zealand, since that's where I was doing this experiment, and we found it to be approximately 58 microteslas. The data is graphed on a logarithmic scale, as it's easier to calculate in. It's a more linear relationship. The graphical equation is the same as the equation here in the bullet points. So we could find x as to be in. And that's how I calculated in earlier on. We found it to be about 3, or in this case -3, which lines up with the dipole equation being 1 over r to the 3. As I moved the magnometer closer to the dipole, the net field in the x direction increased, and when the magnet was far away, the net field in the x direction would be about 0, assuming it's aligned correctly, because we're trying to cancel out the Earth's magnetic field. I also found the off-axis magnetic field by finding a specific distance away from the magnet in both the x and y directions, and calculated d from the magnometer to the magnet. Then I used Earth's magnetic field to correct my overall B net. It's all shown here in the data table up here. And I calculated mu from this data to be about 17.67 amp meters squared. For the computational model, I first inputted my constants and did my calculations for k and mu, and then I also created each observational axis. This code just shows how I made each r vector using the observational axes and mu and the dipole function that I made earlier. This was a resulting model. The orange arrows are the magnetic fields on axis, the blue arrows are the perpendicular magnetic field, and the purple arrow is a distance d away from the magnet. I'll answer these what-if questions. Firstly, what if I hadn't oriented my experiment to compensate for magnetic north? The Earth's magnetic field would have altered the values of each component of B net considerably. I would have needed to isolate the magnet's field effects on the magnometer, and the best way to do that was to align the phone the best I could with Earth. Secondly, what if I were to stick two identical magnets together? The values of each component of B net would likely have increased. However, the unit vectors and dipole moment would have stayed the same. Thank you for watching my presentation.